Hello everyone, I am Sanjay Hosur, a PhD candidate at the University of Wyoming. Dr. Dongliang Duan is my PhD advisor. We are with the Electrical and Computer Engineering Department. Today I am presenting the detection of small changes in power systems with hardware-in-the-loop testing. Nowadays, there is a lot of emphasis to generate power using clean energy sources, which has taken the interest of a lot of researchers. As with introduction of any new technology, there will be a new set of challenges that come in. In this case, there is always a risk of generation ramping up or down suddenly with increased renewable energy generation sources. The renewable energy sources are not predictable as the conventional sources of energy. This will change the traditional grid operation practices, and to better handle these changes, we need to have a better situational awareness. The situational awareness can be achieved with quick and accurate detection of even the smallest changes in the system operating point, which is what the proposed algorithm will deal with. The hardware in the loop testing has been around for at least the last 5 decades. The hardware in the loop testing has numerous advantages, like the real process can be mimicked under imaginable extreme conditions in a laboratory environment. The advantage is underlined as it has been used in various fields such as flight simulation, missile guidance system, anti-lock braking system, etc. In the context of power system, some examples include the unified testing platform for wind energy generation system, operation and control function of microgrid, photovoltaic control system. Here, the hardware and loop testing is incorporated to take advantage of the fact that the real-time simulations can be carried out. For this simulation, the change in real value of the load is given as an external input to the system. To show the efficiency of the algorithm, the total load has been increased by about 0.055 megawatts over 3 hours with a slope of 5 into 10 to the power of minus 6. The load is varied using the value from the power flow, but only the variance is shown here. The algorithm proposed here is a subspace-driven output-only based change point detection algorithm. The output-only approach has an advantage over frequency response and impulse response based on the modal parameter, which depends both on input and output. The algorithm is formulated using the idea that whenever there is a change in the system operating point, the same is reflected in the signal space. The change can be detected by defining a null space which is orthogonal to the signal space. This null space is not unique but sufficient if one orthogonal space is calculated, as product between the null and the signal space is 0. In reality, the product is close to 0 and based on a predetermined threshold, the alarm can be raised. The detection is further improved by utilizing the information given by the time series of the residue. To implement this, the help of a statistical method called cumulative sum, or QSUM for short, is used. First, the interpretation of the results is explained using a simple two-pole all-pass system. After this, the results from the hardware and loop testing is given. The poles for the simple system were chosen from the Minivac model, a reduced order model of the Western interconnect. The modes were chosen as they had frequencies close to each other, that is the Minivac BC and the Minivac Montana modes. In the figure to the left, the residue of all the 5 channels is shown. We know that it is a two-pole system and therefore we can see deviation in 4 channels. As you can see, the channels have both positive and negative deviation, which has led to requiring 2 tests. So the first test will be checking for an increase in mean while the other one checks for a decrease in mean. The alarm is raised based on the channel and the test that responded first. The key equations for the 2 tests are shown here, and in this the yn is the residue, and here there's a factor Vm, that is the minimum jump magnitude, and the threshold lambda, both of which are predetermined. This on the top looks like complicated as we now have 2 parameters to tune, but it is relatively easy as both the minimum jump magnitude and the threshold are very well decoupled. The graphs on the right show the QSIM decision statistics that corresponds to the equation of Gn, and Here we can observe that the statistics remain 0 until the change point, and they either increase or decrease based on which test we are running. Again, since we are using multiple channels and two tests in parallel, we will use an OR rule to declare the change that is raised from whichever channel that is responding first and whichever test that is responding first. Coming to hardware in the loop testing results. The system used for hardware in the loop testing is a 39 bus system with the system order chosen as 40. Thus, we should expect a lot of lines on each graph which will look very cluttered, and the graph would be difficult to interpret. Thus, for the hardware in loop testing, the results from the channel and the test that responded first only are shown. The leftmost figure in this slide shows the frequency deviation between two buses of the system. As soon as you see this, you would probably conclude that the system is in a stable condition, as there is no much deviation and everything looks as it is supposed to be operating in the normal ambient condition of operation. But the plot of the residue, that is the middle figure, shows that this is not the case. Again, for recollection, the load ramping was from 1.5 hours to 5 hours, with the profile of which was shown in the earlier slide. And here we see that there is a little delay in detection in the second figure due to the fact that there is a window of data that we use, and that window also has a memory, so which takes some time to update. And again, to be precise, this change is a very negligible change, so it takes some time before it can be detected. In the graph on the right shows the QSUM decision statistics. Again, we see there is a little more delay over here. This is due to the fact that there is some processing overhead when we convert the residue into the QSUM decision statistics. Now, moving on to the conclusions and the future work, we see that the algorithm is able to detect most of the system operating conditions well, including the subtle ones. The algorithm has been applied to different scenarios, and it has detected the change with almost no knowledge about the system, as this is an output-only based algorithm. Next steps would include testing hardware in the loop testing with a larger system, such as the IEEE 118 bus system, and in the meantime also trying to reduce the delay of detection further. Thank you.